Preparing for a security engineering at GitLab interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you threat model a new GitLab feature? I begin by identifying sensitive assets, users, services, and trust boundaries, then map data flows and external entry points. I use Stride to find spoofing, tampering, information disclosure, and other abuse cases. Next, I rank threats by likelihood and impact, propose preventive and detective controls, and assign owners. For a GitLab feature, I would include repository data, runners, tokens, and integrations. I document assumptions and revisit the model whenever architecture or requirements change. While answering, focus on assets, trust boundaries, data flows, entry points, abuse cases, Stride categories, risk ranking, mitigations, residual risk, and how you would keep the model updated throughout the development lifecycle. Question 2. How would you secure a GitLab CI/CD pipeline? The main risk is that pipeline code executes with valuable credentials. I would use ephemeral, isolated runners, restrict protected variables, pin actions and dependencies, and grant job tokens only required permissions. Secrets should come from a managed vault, never source code, and artifacts should be integrity checked. I would separate trusted and untrusted workloads, require approvals for production deployments, and monitor runner behavior. Security controls must preserve developer feedback speed rather than create bypass incentives. Make sure to cover runner isolation, least privilege tokens, protected branches and variables, dependency pinning, artifact integrity, secret masking, approval gates, pipeline permissions, monitoring, and the risks of untrusted merge requests. Question 3. What is the difference between authentication and authorization, and how would you implement both securely? Authentication answers who a user is. Authorization determines what that identity may do. I would support strong authentication such as SSO, MFA, and carefully managed sessions, then evaluate authorization server-side on every sensitive request. Roles should follow least privilege, with explicit deny by default behavior and separate administrative permissions. For tokens, I would validate issuer, audience, signature, expiry, and scope. I would also log decisions and provide revocation for compromised sessions or credentials. In your answer, distinguish identity verification from permission decisions, discuss MFA, sessions, OAuth or SAML, RBAC and ABAC, deny by default behavior, token validation, revocation, auditing, and privilege boundaries. Question 4. How would you prevent secret leakage in source code and C logs? I would combine prevention, detection, and response. Secret scanning should run in developer workflows and on every push, using provider patterns, entropy checks, and tuned allo lists. Credentials belong in a secret manager, while C masking is only defense in depth because transformed or echoed values can bypass it. If a secret appears, I would revoke and rotate it immediately, identify access, remove it from reachable history where appropriate, and notify affected owners. Prevention must not replace rapid containment. Be sure to mention pre-commit and server-side scanning, entropy and pattern detection, secret managers, masking limitations, rotation, historical cleanup, false positives, access controls, and incident response after confirmed exposure. Question 5. Describe how you would investigate a suspected compromise of a GitLab runner. I would first isolate the runner without destroying volatile evidence, preserve logs and snapshots, and identify jobs, projects, credentials, and network destinations involved. I would review process execution, file system changes, container escapes, artifact contents, and runner registration events to build a timeline. Exposed tokens would be revoked and downstream systems checked. After eradication, I would rebuild the runner from a trusted image, validate controls, communicate impact clearly, and add detections for the attack path. Focus on containment, evidence preservation, runner identity, job history, network connections, credential exposure, artifact analysis, timeline construction, eradication, recovery, and improvements to isolation and monitoring. Question 6. How would you secure a multi-tenant SaaS application like GitLab? I would treat tenant isolation as a property requiring multiple independent controls. Every request must authorize the tenant context at the object level, not merely trust a project or user identifier. I would enforce database policies where practical, separate caches and queues logically, encrypt data in transit and at rest, and restrict support access with approvals and auditing. Automated cross-tenant tests should run continuously. I would also address noisy neighbors through quotas and resource isolation. Discuss tenant isolation, object-level authorization, database controls, encryption, cache and queue separation, noisy neighbor risks, administrative access, cross-tenant testing, logging, and defense in depth across application and infrastructure layers. Question 7. What is your approach to finding and fixing an IDOR vulnerability? An IDOR occurs when a user can alter an object reference and access another user's resource. I would reproduce it with two accounts, changing identifiers while preserving the authenticated session, then confirm the boundary violation. The fix belongs server-side. Load the object through an authorized tenant, project, or ownership scope rather than trusting the request parameter. I would add regression tests for every role, review related endpoints, avoid relying on opaque IDs, and monitor suspicious access patterns. Make sure to explain identifier manipulation, server-side authorization, ownership and membership checks, indirect references, negative testing, regression tests, logging, disclosure decisions, and why obscuring identifiers is not sufficient. Question 8. How would you design secure handling of personal and repository data? I would classify data first, distinguishing credentials, personal information, source code, metadata, and public content. Collection and retention should be minimized to a documented business need. Sensitive data requires encryption in transit and at rest, with tightly controlled keys and audited access. I would design deletion and backup expiration workflows, restrict exports and integrations, and review regional storage obligations. Privacy and security controls should be built into the feature design, not added after deployment. In your answer, cover data classification, minimization, retention, encryption, key management, access reviews, backups, deletion workflows, regional requirements, logging, privacy by design, and controls for exports and integrations. Question 9. How do you prioritize vulnerabilities discovered through SAST, DAST, and dependency scanning? Severity is a starting point, not the final decision. I combine impact with exploitability, internet exposure, authentication requirements, data sensitivity, reachability, active exploitation, and compensating controls. A remotely exploitable dependency issue in a production service outranks an unreachable high-severity finding. I would validate scanner results, assign clear owners and deadlines, track exceptions with expiration dates, and measure remediation trends. The goal is reducing meaningful risk while keeping findings actionable for engineering teams. Discuss exploitability, impact, reachability, asset exposure, EPSS or threat intelligence, false positives, remediation SLAs, compensating controls, developer ownership, and risk-based prioritization instead of severity alone. Question 10. How would you respond to a critical vulnerability reported by an external researcher? I would acknowledge the report quickly, move details to a controlled channel, and reproduce it with minimal access. I would assess affected versions, exploitability, customer impact, and whether exploitation is occurring. Then I would coordinate engineering, infrastructure, communications, and legal stakeholders on containment, patch development, testing, and disclosure timing. Mitigations might include feature flags or configuration changes before a full fix. After release, I would document lessons, credit the researcher when appropriate, and verify remediation. Be sure to mention triage, reproducibility, severity assessment, secure communication, coordinated disclosure, affected versions, mitigation, patch validation, credit, legal considerations, and post-incident learning. Question 11. What controls would you use to protect GitLab runners from supply chain attacks? I would establish trusted, signed runner images with reproducible builds and frequent patching, then run jobs ephemerally so compromise does not persist. Dependencies and build tools should be pinned and verified through checksums or signatures. Network egress should be restricted, and jobs should receive short-lived workload identities instead of broad static credentials. I would verify artifact provenance before deployment and monitor for unusual downloads, privilege changes, or credential access. Supply chain security depends on both prevention and traceability. Focus on trusted runner images, provenance, signing, ephemeral execution, dependency pinning, restricted egress, workload identity, artifact verification, admission controls, patching, and detection of unexpected behavior. Question 12. Explain how you would prevent SSRF in a GitLab integration. I would avoid accepting arbitrary URLs where possible and prefer a strict destination allo list. If user-controlled URLs are required, I would parse them with a trusted library, resolve DNS, reject loopback, private, link local, Unix socket, and cloud metadata targets, and revalidate after redirects and connection establishment. IPv4 and IPv6 must both be covered because simple string checks fail. An egress proxy, response limits, and network segmentation provide additional defense against bypasses. Cover allo lists, URL parsing, DNS rebinding, redirect handling, private and link local addresses, IPv4 and IPv6, metadata services, egress proxies, response limits, authentication, and validation at request time. Question 13. How would you secure webhook delivery and prevent replay attacks? I would sign a canonical request containing the payload, timestamp, and relevant headers with an HMAC secret. The receiver verifies the signature using constant time comparison and rejects timestamps outside a small replay window. A nonce or delivery identifier stored temporarily prevents duplicate acceptance. HTTPS protects transport, while key rotation requires overlapping verification keys and clear ownership. Retries should use delivery IDs so consumers can implement idempotency. Verification failures should be observable without exposing secrets or payload data. In your answer, discuss HMAC signatures, canonical payloads, timestamps, nonces, replay windows, secret rotation, HTTPS, delivery retries, idempotency, endpoint validation, and careful handling of verification failures. Question 14. How would you implement Zero Trust access for a remote-first GitLab workforce? Zero Trust means no implicit trust based on network location. I would centralize identity with SSO and phishing-resistant MFA, issue short-lived credentials, and evaluate device posture and session risk continuously. Access should be least privilege, resource-specific, and segmented so one compromised account cannot reach everything. Administrative actions need stronger authentication, approval, and audit trails. Because GitLab is remote first, controls must work over the public internet and remain practical, with secure recovery paths that do not become bypasses. Make sure to cover continuous verification, identity provider integration, device posture, least privilege, short-lived credentials, network independent access, segmentation, session risk, logging, and usable recovery procedures. Question 15. What would you include in a secure code review for an API change? I review the API's trust boundaries before reading implementation details. I verify authentication, object-level authorization, validation of types and limits, safe handling of errors, and protection against injection or excessive resource use. I check whether responses expose secrets or unnecessary fields, whether state-changing operations are idempotent, and whether rate limits fit the abuse model. I expect positive and negative tests for every role. Finally, I confirm logs support investigation without recording credentials or personal data. Discuss authentication, authorization, input validation, output encoding, rate limiting, error handling, sensitive data exposure, state changes, idempotency, abuse cases, logging, tests, and backwards compatibility. Question 16. How would you improve security culture without slowing GitLab developers down? Security scales through usable defaults rather than constant manual review. I would provide secure libraries, templates, C components, examples, and automated checks that give developers fast, specific feedback. Gates should be risk-based, while low-confidence findings become advisory or are tuned away. Security champions can connect teams with specialists, and threat modeling should happen early for meaningful changes. I would measure remediation time, repeat vulnerabilities, adoption, and developer satisfaction, then improve the experience from that data. Focus on developer enablement, paved road libraries, automated feedback, threat modeling support, risk-based gates, clear ownership, documentation, security champions, metrics, and reducing repetitive false positives. Question 17. How would you design detection and response for suspicious account activity? I would collect authentication, token, API, administrative, repository, and pipeline events with consistent identities and timestamps. Detections should combine signals such as unusual token use, privilege changes, mass repository access, impossible travel, and abnormal runner activity rather than rely on one heuristic. Alerts need asset and user context, severity, and response playbooks. Analysts should be able to revoke sessions, disable tokens, and preserve evidence quickly. I would test detections with tabletop exercises and controlled simulations. Be sure to mention useful telemetry, impossible travel limitations, token and session events, privilege changes, anomaly detection, alert enrichment, severity, containment, privacy, and testing through simulated incidents. Question 18. What is the secure way to manage encryption keys in a cloud environment? I would keep root and wrapping keys in a cloud KMS or HSM and use envelope encryption for application data. Services receive narrowly scoped permissions through workload identity, never embedded credentials, and key usage is logged. Rotation should be planned so old ciphertext remains decryptable during migration, while deletion requires safeguards and approval. I would separate key administration from data access, test recovery procedures, and monitor unusual decrypt activity. The design balances cryptographic strength with operational recoverability. Cover KMS or HSM usage, key hierarchy, separation of duties, envelope encryption, rotation, access policies, audit logs, backup and recovery, deletion safeguards, and avoiding application-managed plaintext keys. Question 19. How would you evaluate the security of an open-source dependency before adoption? I would assess whether the package comes from a trusted source, has reproducible or verifiable releases, active maintainers, responsive vulnerability handling, and a reasonable dependency tree. I would review permissions, build scripts, recent ownership changes, known advisories, and license compatibility. The package should be pinned and scanned continuously, with updates tested through automation. For high-impact components, I would sandbox execution and define an exit plan in case maintenance stops or compromise is suspected. Discuss provenance, maintainer health, release history, vulnerability records, transitive dependencies, license implications, build process, permissions, reproducibility, sandboxing, and a plan for updates or abandonment. Question 20. Tell me about a security improvement you led and how you measured its success. In one role, I found long-lived cloud credentials exposed to broad C jobs. I partnered with platform and development teams to replace them with short-lived workload identities, restrict permissions, and add detection for legacy usage. We rolled out by service, monitored failures, and maintained a temporary exception process. Within 2 months, credential lifetime and privilege scope dropped substantially, while deployment reliability stayed stable. The key lesson was pairing strong controls with migration tooling and transparent operational metrics. In your answer, use a clear situation action result structure, explain the original risk, stakeholder alignment, technical design, trade-offs, rollout, measurable outcomes, and what you learned or would change. If you are still with us, congratulations, You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.